Yes.
Yes, sir.
Screen is visible.
Yes, sir.
Yes, sir.
Fine. Okay, good morning, students. We'll start the today's class. In the previous class, we have studied about tri-state buffers, and I have given you a brief overview about the read-only memory or the ROM, right? And already I have told you basically ROM consists of array of semiconductor devices that are interconnected to store binary data, binary numbers. And unlike the other memories, once the data is stored in the ROM, it can be read any number of times, but it cannot be, what you can say, changed under normal operating conditions, right? And we have discussed about the three types of, I have told you there are three types of ROM. Can anybody remember what are those three different types of ROMs? Yes? The three different types of ROMs are? Anybody remember at least what are those three different types of ROMs I have told in the previous class?
Yes, sir.
Yes?
So masked ROM, PROM, and EROM.
Okay.
EPROM.
EPROM. Yeah. Mask programmable ROM, and electrically erasable programmable read-only memory. And I have told you what is the general structure of the ROM. Now here in this chapter, what we have to study is, we are not going to study in detail about what are the different types of ROM is constructed, how it stores the data, how data is retrieved and all. Our aim here is to use this read-only memory to implement some binary functions or Boolean functions, like how we have seen how decoder can be used to implement Boolean equations, or how multiplexer can be used. Exactly in the same way, read-only memories can also be used to implement some Boolean functions. So how that can be implemented using ROM, that's what we are going to study here. So I think you can see there on the screen what I have shown. There is one ROM example shown, and it is an 8-word by 4-bit ROM. 8 by 4 ROM means what? There are 8 locations, and each location can store how many bits of data here? The ROM which I have shown here has 8 memory locations, and every memory location can store how many bits of information?
4.
4 bits of information. And since this ROM has 8 memory locations, to access these 8 memory locations, how many address lines you need?
Three address lines.
3 address lines. That's why we have shown those are called as input lines or address lines, right? The 3 address lines or input lines are shown, that is A, B, C, and using these 3 input lines or address lines, we can access 8 memory locations, and each memory location is of 4-bit. So those 4 output lines are shown there by letters F0, F1, F2, F3. Is that clear? And it is shown that one particular example is taken, and here what are the contents of those 8 memory locations that are shown? What is stored in the first memory location? Yes. What is stored in the first memory location? Yes. The first memory location is accessed by the address 000. Like that, the last memory location can be accessed by the address 111. Already some data is stored. Data stored in the ROM is shown there, and I am asking what is stored at the first memory location whose address is 000.
1010.
1010.
Yes, exactly. 1010 is the content of first memory location. Then I may ask how it stores 4-bit, because as I already told, every memory location can store 4 bits of data, right? So 1010 is the content of first memory location. Like that, what is the content of the last memory location?
0101.
0101. This is, we can call it as a truth table of the ROM. I hope it is clear. All of you have understood this, how exactly ROM can be used to store the data. Okay, right? So here I have shown these are the 3 input lines or address line, and here the word size is 4. There are 8 words and size of word is 4 bits. So 4 output lines are shown, F0, F1, F2, F3. So with 3 address lines, we can get these 8 input combinations, or these are called as 8 addresses of the 8 memory location. First memory location having address 000 stores 1010. The memory location with the address 100 stores 1100. Like that, the last memory location with the address 111 stores 0101. Fine. Now, what exactly is this read-only memory? In brief, whatever I explained is written here on this particular slide. For each combination of input values on the 3 input lines, the corresponding pattern of zeros and ones appears on the ROM output lines. And that's what I said for ABC equal to 010. You can see here for ABC equal to 010, the ROM content is 0111 that can be read from what? The output lines. Each of the output pattern that is stored in the ROM is called as a word. Right? And this ROM size is called as 8 words by 4 bits. Now, a typical ROM is shown here. Here I have shown how many input lines of the address lines? Yes? N address lines are there. Since there are N address lines, now it can have how many memory locations? With N address lines, you can access how many words or how many memory location? Yes? 2 to the power N. And here, each memory location, out of this 2 to the power N memory location, each memory location stores how many bits?
M bit.
M bits. So you will get how many output lines? M output lines. So a ROM having N input lines, M output lines can store 2 to the power N words, and each words will be of M bits. Is that clear? When I say read-only memory with N inputs and M outputs, what information you will get from this? Yes? When you say read-only memory with N inputs and M outputs, it implies that there are 2 to the power N words or 2 to the power N memory locations, and each memory location can store how many bits of information? M bit of information. That's what is shown here. You can start from 000, all zeros, to all ones, and every memory location can store M bit of information. What to store, it is left to you, and there are different ways in which the data can be stored, and accordingly we can implement a particular function using the ROM. That's what we need to study. I hope all of you have understood what is the structure of ROM. Is that clear? All of you understood? how exactly the ROM looks like, or what is the structure of the ROM, right? So normally when we use a ROM, how exactly the ROM is used to implement any Boolean equation, the general structure, the basic ROM structure is shown here. Already we have discussed what is the ROM structure. This is the ROM structure which we have already discussed. This, whatever is shown in the block diagram, is this particular structure is having here. But in addition to that, if you want to implement any Boolean function, you need to use what is called as a decoder, and this decoder here acts like an address decoder, right? Already we have discussed decoder will have how many inputs and how many outputs. In general, a decoder will have n inputs and 2 to the power n outputs. So whenever you give n bit input to the decoder, it will be giving it will make one of the 2 to the power n outputs active, and which output of the decoder is active, that particular memory location of the ROM is accessed. That's why compulsorily we need to use this decoder, which is acting here as an address decoder. This address decoder decodes the n-bit address into one of the 2 to the power n combinations, and one of that particular memory location will be active, and the content of that memory location will be read on these m output lines, right? So there are n input lines. Out of these n input lines, we'll get 2 to the power n outputs from the decoder. These 2 to the power n outputs of the decoder are given as an input to the ROM, and since one of the output of the decoder will be active at a time, that particular memory location will be read, and that data stored in the memory location will be available at the m output lines. This is how actually the ROM works. Is it clear? All of you understood what is the importance of using decoder here? Why we need to use decoder? This is the actual ROM structure that can be used to implement any Boolean function or the Boolean equation. So we'll take one example now, and we'll see how a Boolean function can be implemented using ROM. In fact, multi-output Boolean functions can be implemented using ROM. So one such example is shown here. Can anybody tell me how many different functions are implemented here using this ROM? Before that, what kind of ROM we have used? Yes? What is the ROM that we have used here? Kiran, can you tell me what ROM we have used, then how many output functions it is having, and what is that function implemented by each of the output line? Kiran, are you there? Yes, anybody else? What ROM we have used here, what decoder we have used, and how many output functions are there, and how many input variables are there, and what is the function implemented by each of the output line? Yes? Are you getting this or no? Say no reply, so what I should assume? Yes? There should be active involvement from your side. Just you should not be physically present in virtual mode. Yes, Sana, are you there?
We are using 3 address lines ROM.
Okay.
So 3 raised to 8 decoder.
3 to 8. Okay. Not 3 raised to 8. 3 is to 8 or 3 to 8. Okay.
So here we are getting 2 raised to n output.
2 raised to n means how many?
2 raised to 3 means 8.
8. Okay. So this ROM is like, what is the size of the ROM here then? What is the size of the ROM? Yes.
32-bit.
32-bit. Size of the ROM you should not tell in terms of bit actually. In fact, I have written there. You can read that. The size of the ROM is already written there at the top.
8
It
word
is
into 4-bit.
8 by 4 ROM. That means 8 word, and each word is of how many bits? 4 bits.
4.
So 8 by 4 ROM. So as you said, it is 32-bit is right. Total memory size is 32-bit. But normally when you tell the ROM size, you have to tell how many words are there and what is the size of each word. So here totally how many words we are having? 8. Here those 8 words are denoted by that M0, M1, F2 up to M7. And each word is of how many bits? Each
4.
word is of how many bits? 4 bits. So this is called as this is the first word M0, then second, third, like that. We have 8th, that is M7. That's why these are called as what? Word lines. These are called as word lines, and these are called vertical are called as the output lines. Now, at the intersection between row and column, you have to put what are called as switching element, like fuses. You have to put a fuses wherever you need a connection. Otherwise, if there is no connection, if you are not put these switching elements, since all these lines are connected to what? All the output lines are connected to what? Through these registers, all the output lines are connected to ground. So, in absence of these switching elements, what will be the output of all these 4 outputs? F0, F1, F2, F3?
0.
0, because they are connected to ground, right? Now, if you connect a switching element, so for a time being, forget about all the switching element. Assume that no switching elements are present except for this particular switching element. Assume only this particular switching element is present and all other are absent. Now, can anybody tell me what is the role of this switching element? What this switching element is doing here? Yes? It is very simple, right? How exactly the ROM can be used for implementing any Boolean function by using the simple fuses or switching elements. What that switching element is doing, which I have encircled, you concentrate only on that. Forget about all other switching elements which are present. Can anybody tell me what that switching element is doing? Yes, Sahana, are you there?
Yes, sir.
Yeah, what that switching element is doing here?
It transfers the signal.
Okay. In simple words, what exactly it is doing?
It's inverting.
Nothing. I told it switching element is nothing but a fuse or a connecting wire. Basically, the switching elements are nothing but the fuses or the connecting wires which connects a particular row and a column. Right. So normally all the output lines are connected to ground. So we got the output F0, F1, F2, F3 as 0. Now I have connected that only one switching element. So this switching element connects the min term M0 with the output line F0. Is that clear? So can you tell me now what will be the output of F0, F1, F2, F3 for this particular case? Yes, Sahana again.
One.
What?
So in ones and zeros, it might be one, like it transfers the signal.
Any other answer from anybody else?
F0 will be A bar, B bar, C bar.
Okay. That means whatever is
F1.
the value of that. If it is 0, you will get 0. If it is 1, you will. Wherever that switching element is there, you will get that particular min term connected to the output. I hope it is clear. So in this case, the output F0 will be A bar, B bar, C bar. And what is F1, F2, F3?
0.
Yes, F1, F2, F3 remains 0. Now assume I have connected this. I'll take one by one example. Now I will add this also. Second switching element I have added. Can you tell me what will be the output of F0, F1, F2, F3? Yes, Sahana? What is F0?
F0
What is
will
F1? What
be
is F2? Yes?
A bar, B bar, C bar,
Yes?
and F1 will be 0.
Exactly.
F2 will be A bar, B bar, C bar, and F3 will be 0.
Yes, very good. Right. So now, can you tell me if I add this switching element also? I have added the 3 switching elements now. Now, what is the output F0, F1, F2, F3?
F0 will be A bar, B bar, C bar plus A
Yes,
bar, B bar, C.
exactly. So why you can
F1
take
will be
plus?
0.
Here you will get now OR operation. If more than one switching elements are connected to a particular output line, then you should take the OR operation of those mean terms. So as rightly said by Sahana, now the output F0 will be A bar, B bar, C bar plus A bar, B bar, C. Because both these mean terms are connected and they will be ORed together to get F0. Now assume that all the switching elements which I have shown there, they are connected. If all the switching elements are connected, now what will be the output F0, F1, F2? Can anybody tell me what is F0, what is F1, what is F2, what is F3? Right, you can tell the answer in terms of SOP form or canonical SOP form also, you can tell very easily here. What is F0? Yes, Sia, can you tell me?
Sir, I did not get it.
You have not understood?
No, sir.
At least you understood about the ROM structure, how the ROM structure will be, right?
Yes, sir.
So to implement any function using a ROM, we have to use a decoder first. So what is the importance of a decoder here? Based on how many input variables are there in your functions, those many inputs should be there at the decoder, and this decoder will generate the output 2 to the power of the number of inputs. So here
Yes, sir.
inputs are 3. So obviously this decoder will generate 2 to the power 3 outputs, and those are nothing but how many?
8.
8 outputs. Right. Now
Yes, sir.
we have 3 input variables. Right. So obviously we'll get 8 input combinations or 8 min terms, but we are implementing here how many output functions? 4.
4.
Why you can implement 4 output functions here? Because the ROM which you are taking, the size of the ROM, each memory location or each word of the ROM can store how many bits?
8 into 4 bit.
Each word can store 4 bits.
Yes,
So
sir.
you can implement 4 functions. For example,
sir.
suppose if you want to implement 6 output functions, you have say like there are 3 input variables and 6 outputs are there in a particular Boolean system that you want to implement. In that case, what should be the ROM size that you should use?
8 into 6 bit ROM.
8 word by 6 bit
6
ROM.
bit ROM.
There should be 8 words, 8 memory locations, and each memory location should be able to store how many bits of information? 6 bits of information. I hope that is clear now here. Here,
Yes,
why
sir.
we have used 4-bit ROM? 8 word by 4-bit ROM, because we are implementing 4 functions. Right. So you can see here array-like structure. This is what is the array-like structure, wherein we have word lines. How many word lines we are having? 8 word lines, and each of these words can have 4 output lines because the size is 4. Right. In the absence of the switching elements, all the output lines which are there, we have connected it to what?
Ground.
Ground through the register. So what will be the output? F0, F1, F2, F3 in the absence
0.
of the switching elements?
0.
Now switching element means what? I told it is a fuse. you are going to make the connection between that particular word line and the output line, or intersection of rows and column you are doing. Wherever you want to have a connection, you have to put the switch. So I'll be putting this. As I said, you consider only this particular switch now. What this switch is doing?
It is connecting M0
M0 to what?
F0.
Is that clear?
Yes,
Similarly,
sir.
what this switch is doing?
It is connecting M0 to F2.
F2, exactly. Similarly, what this particular switch does?
M2 to F1.
F2 to F1. You understood this?
Yes, sir.
Right. Whenever there is a connection, means what? That particular minterm or that particular bit will be made available at the output. Right.
Yes, sir.
Is that clear?
Yes,
So
sir.
now, what is happening here is something is stored here. Like, can you tell me one more thing? What is the content of the first word here? M0. Right. This is first word line. What is
Yes,
stored
sir.
in the first memory location? This is first memory location. What is stored in the first memory location?
So A bar, B bar, C
No,
bar.
no. What is stored in the memory location? When I say memory location, each memory location can store string of zeros and ones, right?
Yes, sir.
So what is stored in the memory location, first memory location or the first word?
So
Because there are
0,
8
1.
words.
Yes,
What
sir.
is stored?
So 0, 1, 0, 1.
0, 1, 0, 1.
1, 0.
Hmm?
Yes, sir.
Means what is stored? What is the 4-bit content of the first memory location?
So 0, 1, 0, 1.
Okay, you are telling which side actually. Oh, we can, if it normally we tell from the MSB. This is our MSB, right? This is LSB. So what is stored here in the first bit? This is connected. Means what? 1 is stored. 1,
Okay.
0, 1, 0. First word is 1, 0, 1, 0.
1,
What
0.
is second word? What is stored in
1,
the second word? Second word is what again?
1, 0, 1, 0.
1, 0. What is stored in the third word?
0, 1, 1, 1.
1. Exactly. Very good. Then next.
0, 1, 0, 1.
Yeah, like that last word stores what?
0, 1, 0, 1.
That is the ROM content actually. Right?
Yes,
If
sir.
this is the content, what are the functions implemented? So wherever there is a connection, that is stored. So what will be F0 expression? I am asking now. F0 will be this or this or this or this, or in canonical SOP form, I can write F0 as sigma m 0, 1,
1,
4, 6.
6. Yes,
The
sir.
function implemented by this ROM F0 is summation 0, 1, 4, 6. Like that, can you
Yes.
tell me what is F1?
Yes, sir. Summation of 2, 3, 4, 6, 7.
7. Good. F2?
0, summation of 0, 1, 2, 6.
6. Then?
F3.
Yes.
F3 will be summation of 2, 3,
Summation
5,
of
6, 7.
2, 3, 5,
5,
6,
6, 7.
7. That's all. These are the 4
Yes.
functions we have implemented using 8x4 ROM. Now
Yes.
at least you understood?
Yes, yes, clear.
What about all other? All of you understood this? Anybody you are having any doubts? You should ask. Is that clear? All of you understood this?
Yes, sir.
Yes. Let's see, no voice from the other people. All of you understood or no?
Yes, sir.
I need some more replies. Don't put it in the chat box because chat box is not visible for me when I am sharing my screen.
Yes, sir. Understood.
Right. Okay, good. Then we'll proceed further. The whatever I have explained, the same thing is put here in this slide. You can just go through it afterwards, and that normally at the output by default you can view like there is a OR gate. Whatever minterms will be ORed to get the output. So here F0 is M0 or M1 or M4 or M6, or the same thing can be written in canonical SOP form as F0 equal to sigma M 0, 1, 4, 6. So that is how it is implemented. See here, all those are written. And then you may ask, how I got this A bar, B bar plus AC bar? Can anybody tell me? How do you get these functions? This what Shreya has told. F0 is this, F1 is this, F2 is this, F3 is this. So how do you get these? Obviously, you can use a K-map, simplify this and check whether you will get this or not. So these are the functions implemented by the read-only memory or the ROM. Clear? Any doubts? Yes?
No, sir, doubts.
Anybody is having any doubts? Okay. The multiple output combinational circuit can be easily realized using the ROM. Right? So I'll give one example. Can you able to design this or realize this using the ROM? What is the question asked here? Realize a code converter that converts a 4-bit binary number to a hexadecimal digit and outputs the 7-bit ASCII code. Now, what do you mean by ASCII code? Can anybody tell me what is the meaning of ASCII, what it stands for, and what exactly is this code? Yes? Akash, are you there? Yes, Rahul.
Yes, sir.
Yeah, what ASCII stands for?
Sir, don't remember, sir.
Don't remember. Anybody who knows what is ASCII?
American Standard Code for
Information interchange.
Yes, exactly. Very good. ASCII stands for American Standard Code for Information Interchange. It is the universal code accepted in the computer industry, and it is how many bit code? It is how many bit code? 7 bit code. That means in ASCII code, every digit, every alphabet, every numeral, every symbol is represented by 7-bit code. For example, if you take the number 0, what is the ASCII code for number 0? Can anybody tell me? Or what is the ASCII value of 0? Yes? Because at least you should know what is the ASCII value of 0 to 9, what is the ASCII value of capital A, what is the ASCII value of small a, so that other characters easily you can get. At least these values everybody should know. ASCII value of 0, ASCII value of capital A, ASCII value of small a. With these 3 values, at least you will be able to derive ASCII code for all the 26 plus 26, 52 alphabets plus 10 digits, that is 0 to 9. So I am asking what is ASCII value for 0? Anybody knows? Yes. The ASCII value of 0 is how much? 48 in decimal. And if you convert that 48 in hex, it becomes how much? ASCII value of 0 is 48 decimal, which is equal to, in hexadecimal, it is how much? 16 3s are 48. So this is decimal. In hex, the ASCII value of 0 is 30. So this 30 is represented in 7-bit code. So what is the ASCII value of 0 in ASCII format? 3 is nothing but 011, then 0, 0, 0, 0. So total how many digits are there, or how many bits are there?
7.
How many bits are here? 7. So this is the ASCII code for what? Yes. This is the ASCII code for what? 0. Like that. If it is 1, what is the ASCII code for 1? 31 hex or 49 in decimal. So you remember in hexadecimal value only, so that easily you can represent it in binary. So ASCII value for 0 is 30 hex. Similarly, can anybody tell me what is the ASCII value for capital A and what is the ASCII value for small a? Yes? ASCII value for capital A is how much?
98. 98.
98. ASCII value for
65.
capital A is 65 in decimal. And that comes to be how much?
41.
41 in hex. Similarly, ASCII value for small a is how much?
97.
7 in decimal. Whereas it is how much?
61.
61 in hex. I hope at least these three values you should remember. You should never forget. Right? ASCII value for 0 is 31 hex. Sorry, 30 hex. ASCII value for capital A is 41 hex. ASCII value for small a is 61 hex. Is this clear? What exactly you mean by ASCII and what is that ASCII code I have explained. But that was not my intention to teach you what is ASCII code. What you have to do is this question. You have to answer this question. What is this question? You need to realize a code converter that converts 4-bit binary number to a hexadecimal digit and outputs the 7-bit ASCII code. That means if I give you say input as 1010, 4-bit binary number I have given, right? What it should give? First it should give me equivalent hexadecimal digit for this. What is equivalent hexadecimal digit for 1010? You are getting, I will be giving you input as 4-bit binary number. Then you have to give me equivalent hexadecimal digit and then you need to output equivalent 7-bit code for that hexadecimal digit. So I have given you example, input is 1010, 4-bit binary number. What 1010 represents in hexadecimal? Yes, 1010 is how much?
10.
10. In hexadecimal, 10 means what?
A.
A.
10 means A. Right? Where is that? Sorry. 10 is nothing but A. Right? So I will be giving you 4-bit number 1010 whose hexadecimal equivalent is A. In turn, the circuit which you are designing or the code converter which you are designing, it should give me output as what? It should give me output as what? Not A. What I should get? 1 0
7-bit.
0 0 0 1. Why I should get this? What is this equivalent? 100 is nothing but what? 4. 0001 is nothing but what? 41. And what is this 41? It is what?
A.
ASCII value of what? A. So this is the code converter that you have to design. I hope all of you getting the question. You have to realize a code converter that converts 4-bit binary number to a hexadecimal digit and outputs what? The equivalent 7-bit ASCII code. This is very important example from your examination point of view. Realize a code converter that converts a 4-bit binary number to a hexadecimal digit. How to do it? Can anybody throw a light on this? How we should go ahead about this? Yes? How we can go ahead about this to implement this code converter? Yes? How we should go about this? At least any idea how we should implement this? I'm not asking the exact answer. I'll give the exact answer shortly. But what should be your approach to solve this particular example? Yes? Aniket?
So no idea, sir.
No idea.
So
That
using
means you have not
decoder.
understood the ROM concept, how it should be used to implement. And I have
So
given you,
first
I
of
have
all,
explained you what the example. So one thing you should remember, whenever you are designing or implementing or realizing any digital circuit, what should be the first step? What should be the first step in designing anything and everything in digital electronics? The first step should be what?
Converting into binary form.
No. First step will be always, you should have what? The block diagram. So you should write the block diagram. They are given, there is a 4-bit binary.
using
Right?
decoder.
And what output you should get? 4-bit binary, and output expected is what? What is the output expected? ASCII code. So how many inputs should be there? 4.
4.
And how many outputs should be there? 7. So this is the block diagram that you have to design. That is the first step in designing any digital circuit. What is the second step? Once you draw the block diagram, the second step in designing is what?
Truth table.
Truth table. So can you write the truth table for this? And once you write the truth table, you can play with it very easily. Whatever form you want to use it, or whatever technique you want to use to implement that, you can use it. So now at least, can you tell me, Aniket, what I should do next? I have given you the block diagram. What is the next step I told? What is the next step I told?
So we have to
Right?
implement the truth table.
Truth table. So can you tell me what the truth table should consist of? What the truth table should consist of?
4 inputs.
4 inputs, and how many outputs?
7.
7 outputs. And that 4-bit input you can represent by one hexadecimal digit first, and then that hexadecimal digit should be represented by what? 7 output lines. That's what is shown here. You can check. Right? So inputs I have represented W, X, Y, Z, A, B, C, D, P1, P2, P3, P4, anything you can write. And the outputs, how many outputs I have shown? 7 outputs. What those outputs are represented as? A0 to A6. So you can see here, the first input is what? First input is what? 0, 0, 0, 0. That is nothing but hexadecimal digit 0. So how that 0 is represented in ASCII? So if you want, you can add here one more column. Write the ASCII value in hex. 0 is nothing but what? It is nothing but what? 30 in hex. 1 is nothing but 31. Like that. 9 is nothing but 39. After 39, it is not 3A, 4, 1, then 4, 2, 3, 4, 5, 6. So 4, 6. These are the ASCII values. Now represent 30 in binary. How do you write 30? So first digit, whatever you are having, it should be represented by 3 bits. So 3 is nothing but 0, 1, 1. And next digit should be represented by 4. Why we have to use 3 here and 4 here? Because ASCII is how many bit code? ASCII is how many bit code? 7 bit. ASCII is 7-bit code. So first digit what you get in the hexadecimal digit, that should be represented by 3 bit. So 3 is represented by 011. I am not writing 0011. If you use 4 bit, you have to write 0011. So 3 bits we have to use. So 011, then 0. 011, 1. 011, 2, 3, up to 3, 9. And then 4. How do you represent 4? 100. And 1 is what? 0001. Similarly, 4 is 100, 6 is 0110. So 4142, 43, 45, 46, and then you can implement that. So you have got A0, A1, A2, A3, A4, up to A4 I have shown, and then whatever A4 you can see here. This is what is A4. A4 and A5 are same, no change. Right? A4 and A5 are as it is. So I have shown A4 equal to A5. And if you observe A6, what is the relationship between A6 and A4 or A6 and A5? A6 is what? Complement of A4. A6 is complement of A4. So the complement, that is a NOT get added, and we get, this is the block diagram for the what? Read-only memory to implement a code converter which converts 4-bit binary number to hexadecimal digit represented in ASCII form. That is how we can implement it. The realization of this, what is shown now, is if you want to implement it using a ROM, I told you have to put those switches. So in between you have to put the switches. So you have to use here, which decoder you have to use first? How many inputs are there?
4
How many
inputs.
inputs you are having? 4. So which decoder you will be using? 4 to
4 is to 16.
4 to 16 decoder. So there will be 16 output. To get this A0, which all output you need to connect? Which all output you need to connect to get the A0? You can see here. Second, then fourth, then sixth, 8, 10, 11, like that. All these should be taken, and you have to put the switch there. Here you have to put the switch, here you have to put the switch. Wherever 1 is there, you have to put the switch, and wherever 0 is there, you have to leave it open, and that is what is shown. Instead of showing a switch now, what I have shown? What is shown here? The X mark indicating there is a connection. So it is similar to the previous diagram which I have shown. Because to draw the diagram, it becomes a bit complicated, so I have made it it is simplified, and switch is shown by X. So X indicate there is a connection, and if there is no X, there is no connection existing between that row and column, right? So in fact, here I have shown only A0, A1, A2, A3, A4. You can add that remaining 3 also. Why remaining 3 that author has not shown is because it is same. A5 and what is that? Yeah, A4 is there. Remaining 2 are not shown because A5 is same as A4 and A6 is complement of A4. But you need not delete those 2. You can add 2 more columns also. A0, A1, A2, A3, A4, A5, A6, and you can show the X mark wherever there is a 1. And wherever there is a 0, don't put that X mark, and that's how you can complete the realization of a code converter. I hope all of you have understood this. Again, I am repeating, this is very important example from examination point of view. Any doubts here? All of you understood? Say at
Yes,
least yes or no. If you are not understood, you go through
Yes,
it
sir.
once again. Right? So if you understood, as a homework, you just try to do this. You can just take down this example and you can try to do it. With this, we have completed the discussion on the ROM. One more concept is remaining, programmable logic devices, which we'll be discussing in the next class. So before you leave, I want all of you just take down this example and try to implement this. Everything is given in fact here. Just you have to write what are F1, F2, F3, F4. In fact, they ask only for F1 and F2. So you can write what are the values of F1, F2, F3. For a particular input also they are given. What happens if A0, B is equal to 1, C equal to 1? What output you are going to get here for at F1, F2, F3, F4 you have to tell. And then you have to write what is the expression, min-term expression for F1 and F2. I hope everything is clear about the ROM. Any doubts? Sohan?
Yes, sir, clear.
Clear? Okay. If everything is clear, we will stop for the day then. Right. Just go through this concept once again. This is very important concept from your examination point of view. So I want each one of you should go through it once again